Okay, I have a particle traveling in uniform circular motion with a speed of v on a circle of radius r, and I started time here at an angle of 0. At t equals 0, there's no loss of generality from describing a spinning object this way. And at this point in time, the object has traced out an angle of theta. Well, if I write down the angular velocity, and then plug in that theta naught and t naught are both equal to 0, then that means my angle theta at any point in time is just omega t. So I could replace this with an omega t. All right, then I want to look at some of the trigonometry that's going on. I want to get the formal equations of motion for this particle traveling in a circular path, and that means I need to have the x-coordinate as a function of time and the y-coordinate as a function of time. But it looks like those are just given by trig functions. So this is just an r cosine theta down here, where theta is omega t. This is an r sine theta, where theta is omega t. So real quick, I have the equations of motion for uniform circular motion. And that is x of t equals r cosine omega t, and y of t equals r sine omega t. And if you have that, you have everything about this motion, and our main goal today is to get the centripetal acceleration formula. So physics books traditionally do this using algebra, but it just seems like such a clunky tool when we have the ability to use calculus to do it. So let's just do it. So I have a position vector, and that is actually at any point in time pointing at the location of the object from the origin. And the position vector is given by x of t I hat, so r cosine omega t I hat, y of t j hat, so r sine omega t j hat. All right, then I can apply a time derivative to this thing and find the velocity vector as a function of time. So v of t, if I differentiate this, I get negative sine omega t, and then the chain rule forces me to multiply by an additional omega. So I have negative r omega sine omega t I hat. This one, positive r omega cosine omega t j hat. Finally, what I'm after here is the magnitude of the acceleration. So I differentiate one more time. And again, the chain rule produces a factor of omega out of this, and I end up with an r omega squared. So I have negative r omega squared cosine omega t I hat, and this one produces a minus sign and another omega. So there's my acceleration vector. It's just a matter of finding the magnitude of it. So to get the magnitude, I take the components, square them, and add them under a square root sign. So I end up with the magnitude of A as a function of time. There's not going to be any time dependence, but I should write it that way for completeness. And I get r squared omega to the fourth cosine squared omega t plus r squared omega to the fourth sine squared omega t. And I can factor out the r squared omega to the fourth out of each of those terms and square root it, and it will come out in front as an r omega squared. Square root cosine squared omega t plus sine squared omega t. And hopefully you recognize that identity. If you take cosine squared of an angle, add it to sine squared of the same angle, you get 1. So finally I have the A, all the time dependence having vanished. The magnitude of A is just r omega squared. Okay, so now I need to do a little bit of manipulation. It's not that this isn't useful. It is frequently useful when we're looking at rotation. But I want to modify it by using the formula relating linear and angular speed, v equals r omega. We're going to solve that for omega and get v over r. Replace it in here, and I get v squared over r squared. So a equals r times v squared over r squared. One of the r's cancels, and I've got my classic formula for the centripetal acceleration. So finally I wanted to talk about the direction of the centripetal acceleration and why it's called centripetal. And first off, we know that the speed never changes here, which means the acceleration vector has to be perpendicular to the velocity vector. And that just gives us very limited choices on which way it could point. So I could have an acceleration vector that points that way, or I could have an acceleration vector that points this way. And all I have to do is think real quick how each of these would influence the change in the velocity vector in the next small time increment. So I'll just do that down here. If I just look at finite time changes, I know that A, or A average, is delta V over delta T. That means the change in the velocity vector is given by the acceleration vector scaled by a factor of delta T. So if I had an outward pointing, I think I'll just do it like this. If I had an outward pointing acceleration vector, it would cause a change in the velocity that points in that same direction. So what would that look like? I would have a little delta V pointing in the same direction as A, and my new V would be curving away from the center of curvature. So if I had an outward acceleration, my particle was going to spiral off this way. That can't be right. Just to be thorough, we could look at the case of the inward acceleration. That would cause a change in velocity in the same direction as A. And then when I draw my new velocity vector a moment later, it is turned to the left. Of course, a moment later, I'm up here, so it could still be tangential. All right, so what I do to remind myself is I make the speed argument that the acceleration must be perpendicular to the velocity, otherwise the speed would change. And then I just look at it real briefly. I ask myself, which way does it have to point to rotate the velocity vector the way that this thing is actually moving?